Hey guys, sorry I'm out today. Son woke up sick again, so here I am. Hopefully this goes a little better than last time. So this lesson is mainly when I did it the other day with my other classes. It's mostly a free response question practice day. And with that said, I know it's easy since if I'm not here to just not take it seriously. So what I'm going to have you guys do on the free response questions on the notes, I'm going to have you guys email me what you get after you finish them before you're able to see the responses. So I'm going to post the notes on Canvas. I'll post the rubrics on Canvas. But again, I'm going to have you send me your work before you check the answer. And I'll know if you did, because if you just put what all the right answers are, I'll know, well, unless you're a genius, that you probably just copied the answer. So I'd like to see your own work. Basically, try them. The only way you're going to get better at AP Calculus and AP style questions is by you guys putting in your best effort. And so, but there is one new topic to talk about, and that's why I'm doing a video here. We've mentioned Riemann sums before, sorry, where you can use a left Riemann sum, a right Riemann sum, a midpoint Riemann sum. And that's what we're going to do on this problem. We're going to estimate this integral using a right Riemann sum of 4 subintervals of equal width. So what we are going to do is sketch this. And you can sketch it just by graphing it in your calculator. You can use a calculator on this problem, but just not do Math 9. So I'm going to go ahead and graph this. So it goes up to 4. And then it goes out to 4, and it's really just a quarter circle right here. And we're going to do a right Riemann sum of 4 subintervals of equal width. So we're going to put in 4 rectangles, and we're going to start our rectangles on this right endpoint right here. So remember, you're going to start here at the right endpoint, go till you hit the curve, and then go over to the next interval. Well, you hit the curve right away. So that height of that first rectangle is 0. So we're going to have A equals, our width is 1, so 1 times 0. And then we're going to draw our next rectangle, go up, over, down. And so we're going to have 1 times whatever we get when we plug 3 into the function. So we have to find f of 3, essentially. Well, that's why they give us the function here. We plug 3 in, and we would have 16 minus 9, so square root of 7. So 1 times square root of 7. Then at 2, go up, over, down. So we're going to have 1 times whatever f of 2 is. So 16 minus 4 is 12, square root of 12. And then do the same thing. So nothing new. What we're doing here is nothing new. So we're going to have there, what? F of 1, so square root of 15. And if it's free response, you just leave that answer. You don't need to do anything with it. But if you did want to take out your calculator, it would be 9.983. Okay, so we've talked about that. But it's a terrible, terrible approximation because you look at all this missing area. We're missing all that, this big chunk here, this stuff up here. We're missing a lot of stuff. So it's not a great approximation. In fact, this has come up through discussion, but there is a better shape that we could plug in, and that would be trapezoids. You'll see why trapezoids better fit curved regions here in a second. But typically, when you're doing an estimation type problem, trapezoids are going to be the way to go. And we haven't talked about it yet, but that's what we're going to do right now. We're going to use trapezoids to approximate. Now, some people always say, well, if trapezoids are better, why even do the rectangles? The reason that Riemann sums and rectangles have to be talked about is because that is where integration comes from. The definition of integration comes from adding up infinitely many, infinitely small rectangles. So that's what integration is actually doing. It's doing Riemann sums. But if we're doing an approximation or an estimation using geometric figures, then trapezoids are going to be the way to go. And so let's see why this is better. Let's take that same function, same interval, and draw it again. So we'll go out to 4, up to 4. It's beautiful. It's a beaut, Clark. Okay, so now look at why trapezoids are going to fit better. It doesn't matter where you start. There is no left trapezoid or right trapezoid. There's a trapezoidal approximation because if you're dealing with 4 subintervals, you're going to fit 4 trapezoids in here. Right or left doesn't matter. So let's say we start here. Let's go up. All right. Now we're going to go till we hit the curve at this point. We're going to draw our trapezoid straight to where our function would hit the curve at f of 1, and then go down. Now that kind of looks like a horizontal line, but it's not. It was slanted because that function is below where that function is. So it is kind of a slanted piece right there. Well, let's do the next one. Go up at 1, and then let's go down at an angle, and then down. Create another trapezoid. Then do the same thing. Go up, and instead of going straight across, you go down and connect it down, and then up. Now this one's interesting. You go up, and then you go down right here. So this is actually going to form a triangle, but we could still use our trapezoid formula. You'll see why. So now look at why these 4 trapezoids, we're only missing out on that itty-bitty area. This is a much better approximation than these 4 rectangles up here. So the only thing we need to know is the area for a trapezoid. Because what we're going to do is essentially, just like we found the area of 4 rectangles up here and added them, we're going to find the area of 4 trapezoids here and then add them together. So the trapezoid formula, if you'll recall, is 1/2 times the height times the sum of the bases. And we're just going to do that formula 4 times. So we have to understand what the height and what the bases are. These trapezoids are set up in a way that are a little different than your normal looking trapezoid. Like you guys are used to looking at trapezoids that do this. Right? You have your 2 parallel sides, typically top and bottom, and that's your normal looking trapezoid. Remember, the bases are the 2 parallel sides. And so if you look over at these trapezoids, the bases are actually the vertical segments, not the bottom right here. So the height, while the height is typically your vertical segment right here, on these, your height is actually the width of these trapezoids right here. And think about why. So let me look at this. Let's say I take one of these trapezoids and flip it. All right, so I just took one of these trapezoids and just flipped it right over here. So notice that pretend like this is this trapezoid right here. Okay, and that's your slanted side. So your height would be this perpendicular segment that connects the bases. That's this right here. So your height is actually your delta x, whatever you're changing the x is. And your bases are the 2 vertical lines. You're going to add those together for each one. So okay, so let's do this. Let's practice this. So let's say I want to find the area of this first trapezoid. Okay, I want to find the area of this trapezoid. So I would do 1/2 times the height. Well, the height is our change in x right here. So in this case, our height is 1. And now we need to add these 2 vertical segments. So we need to add whatever f of 0 and f of 1 are. Well, f of 0 is 4. F of 1 is square root of 15. I need to grab my calculator. So I'd have 4 plus square root of 15. So 7.873. And that's what I get from adding these 2 bases together. This is the area of this first trapezoid. Plus, now let's add the area of the second one. So we would do 1/2 times the height, which again is 1. And then add f of 1 and f of 2 together. So the height at 1 and the height at 2. So we'll be adding, let's see, 1, so square root of 15 plus the square root of 12. And you're going to get 7.3371. That's trapezoid 2. And then just keep going. Trapezoid 3 would be 1/2 times 1 and then add these two together. So that would be 6.1099 plus, do the last one. Now the last one is a triangle, but you could treat it the same way. You can use your trapezoid formula. You can still do 1/2 times the height, and then the sum of the bases, well, you would have f of 3, this y value, and then 0. So your other side is just 0. And you're adding them, so it's just you're adding nothing. And you get 2.6458. If it's free response, you leave all that nonsense and move on. But if you add it all up, you get 11.983. So trapezoids are just like Riemann's, just a little harder formula, but you're doing the same thing. You're finding the area of all 4 trapezoids, adding them up. One other example, real quick, because the other two are just you doing free response questions. The application integration, we've already done this. I just wanted to make sure I talked about it one more time. It says a helicopter is rising straight up in the air. Its velocity at time t is 2t plus 1 feet per second. How many feet does the helicopter rise between t equals 2 and t equals 6 seconds? And remember that when you integrate a rate, you get back to the change in the actual thing the rate's talking about. So if we're integrating velocity, we get back to change in position. And so when we integrate velocity, in this case 2t plus 1, from 2 to 6, this is going to get us the change in position from 2 seconds to 6 seconds, which is what we're trying to find. We're trying to find how far the helicopter rose from 2 to 6. So that's just what we're going to do. So we'll use our fundamental theorem of calculus. So we get t squared plus t. Plug in 6. Minus plug in 2. So you get 36 feet. Okay, so like I said, what you have to do now is this free response here. All right, I would take, the way I would handle these, I would take maybe 10 minutes or 7 minutes or whatever you think, and then maybe converse and work together. It's the only way you're going to get better. And then check the rubric that I'll have posted on Canvas and see where you get your points. And then you're going to have this one. This is a full-blown, all 4-part free response question. So I would try to take 15 minutes to do this. I gave this 15 minutes in my other class, and they needed it. And then maybe talk to each other and see how you do. These are both calculator active. You can use your calculator on both free response questions. So keep in mind what that means you could do, and then check the rubric. But I would like you to email me both free response questions, so you could do them both on the same Notability, notes, whatever. Just I want you to email me what you have done before you check the rubric. All right, that way I can kind of see where you're at in terms of understanding. All right, good luck.